We are currently discussing normal forms. Normal forms arise when we come to address the issue of redundancy and decomposition of databases. We have discussed various normal forms in the previous class. The first normal form is the simplest one, in which states that all attributes must be simple. They cannot be nested attributes. That is, attributes may not contain sets of attributes inside an attribute. The second normal form is one which is in first normal form and which contains some additional properties which try to prevent redundancy. We define the second normal form as follows. A relation R is in 2NF or second normal form if every non-prime attribute of R is fully functionally dependent on each candidate key. An attribute is said to be non-prime if it is not contained in any candidate key. It is said to be functional dependency is said to be fully functional dependent if any element of if any attribute of the left hand side cannot be removed so that the functional dependency still holds. If you cannot do that, it is a sort of minimal left hand side of a functional dependency alpha to beta. It is a sort of minimal left hand side. You cannot just remove any one of them and still the functional dependency will hold on each candidate key. And we saw some examples to how second normal form prevents redundancy. There was the first simple loan scheme example. We had a loan scheme with customer name, loan number and amount. Customer name and loan number gives amount. The candidate key was customer name and loan number. The only non-prime attribute was amount, and since amount is dependent on both customer name and loan number, it is fully functionally dependent. So the non-prime attribute is fully functionally dependent on the candidate key. So this relation is in second normal form. On the other hand, we came to another example with courses, course number, title, location and time. And we found course number, title, and course number and time is location. These are the two functional dependencies. There is only one candidate key. There are two non-prime attributes, of which location and title, of which location is fully functionally dependent on the candidate key, whereas title is not fully functionally dependent because course number itself gives title. Therefore, this is not in second normal form, and therefore we have found that second normal form tries to identify redundant elements. Now we will see another example, which is a new supplied by relationship. It says that for a particular supplier name and for a particular item, the price is fixed. The price of that item is fixed. And it also says that for any item of a particular price, there is an associated gift item. For some items, if the price is 10 rupees, then the gift item is fixed. That is, you will get a toy, or you will get a sachet of something, shampoo or something like that, if you buy an item worth 30 rupees. All items worth 30 rupees have got the same gift item. All items worth for 50 rupees have got the same gift item. This does not mean that for this supplier with this item and this price will have this item, will have this gift item. The gift item is only price dependent. Now let us see what are the candidate keys. The candidate key here is supplier name and item. Because you take the closure of this, you will get price and gift item. So supplier name and item is the only candidate key out here. There is no other candidate key. Therefore, non-prime attribute price and gift item, of which price is fully functionally dependent on supplier name and item. Gift item, since gift item is dependent on price, by transitivity it is also fully functionally dependent on S item and S name and item. Therefore, price is fully functionally dependent on this, gift item is also fully functionally dependent on this. So this relation is in 2NF, but there is still a problem. There is a clear-cut difficulty here. There is an redundancy here. So second normal form is not able to remove all redundancies. This redundancy is a redundancy which second normal form could not remove. Price and gift item. And we saw another example, the banker branch code customer name and agent example, where agent branch code and customer name branch code agent, there are two candidate keys, customer name and branch code and customer name and agent, and there is no non-prime attribute. Therefore, by default it is in 2NF, but there is still redundancy. So redundancy may be there even if a relation is in second normal form. So in order to refine it further, we study what is the third normal form. The crux of the reason for which, or a motivating example for defining third normal form, is this example. Here, gift item is dependent on price. It is fully functionally dependent on S item and price, but it is also functionally dependent on a non-prime attribute. It is functionally dependent on a non-prime attribute. Now that non-prime attribute may be functionally dependent on the candidate keys, which puts this redundancy here. Therefore, to avoid that, the third normal form says a relation is in 3NF if it is in 2NF and no non-prime attribute is functionally dependent on other non-prime attributes. This is the additional aspect which was introduced. No non-prime attribute is functionally dependent on other non-prime attributes. This makes it possible for us to prevent this sort of a thing. Here this non-prime attribute is functionally dependent on this non-prime attribute, bringing in the redundancy. And therefore this is, though it is in 2NF, it is not in the third normal form. However, let us come to this example. This example has got no non-prime attribute, so it is in second normal form. And since it has got no non-prime attribute, it is by default in third normal form as well. This is also in third normal form, because third normal form says it must be in second normal form and a non-prime attribute cannot be dependent on another non-prime attribute. But there is no non-prime attribute here. Therefore, it is still in third normal form, but redundancy is still there. In order to avoid and prevent even this sort of a redundancy, we have a stricter form, which is called the Boyce-Codd normal form. The Boyce-Codd normal form says this: a relation scheme R is in Boyce-Codd normal form or BCNF if for all functional dependencies alpha to beta which hold on R, either one of the two should hold. Alpha is a superset of beta, which is a trivial thing. It does not make any additional input. And if alpha to beta holds, then alpha must be a superkey. If alpha to beta holds, then alpha must be a superkey. Now let us see what is the meaning of this. Let us go back to all our examples one by one. Let us come to this example. It just says if alpha to beta holds, then alpha must be superkey. That's all. Otherwise the dependency is trivial. We did not even write down the trivial functional dependencies. And here it holds. So this is in Boyce-Codd normal form. Let us take the second example. Alpha to beta holds, then alpha must be a superkey. Is alpha a superkey here? No, because there is course number alone is not a candidate key. Therefore, this is not in BCNF. BCNF will immediately catch you if there is some redundancy or the other. Any redundancy in terms of a functional dependency will be caught by BCNF. This one is fine. This satisfies the BCNF property because course number and time is a superkey or a candidate key. But course number to title, this does not satisfy BCNF. Let us see this example. In this example, this satisfies BCNF, but this does not satisfy BCNF. Because this is not a superkey. Let us come to the fourth example. Here, agent to branch code does not satisfy BCNF because agent alone is not a superkey. Therefore, this is also not in BCNF. The core idea of BCNF is this: if alpha to beta holds, then alpha must be superkey. If alpha is superkey, then there can be no redundancy. If alpha is not a superkey and not any candidate key, then obviously redundancy will come into the picture. Therefore, BCNF is a direct way of preventing redundancy. Let us see how BCNF is related to 3NF. What is third normal form? Third normal form says that it is in second normal form. So what does second normal form say? Second normal form says that every non-prime attribute must be fully functionally dependent on a candidate key. That means that if you take alpha to beta, then in second normal form, either alpha is a superset of beta, either this will hold, this may hold, or alpha may give R. Even then, if alpha gives R, alright, if alpha gives all of the relations, then obviously beta is fully functionally dependent on alpha. But what additional things may happen in 3NF? In 2NF? In 2NF we can have non-prime attributes functionally dependent on other non-prime attributes. That is what can happen in 2NF. In 3NF this cannot happen. So in 3NF either this should happen or this should happen, or each attribute in beta must be part of a candidate key. Let us see what is the meaning of this sentence. Let alpha to beta be a functional dependency. Then it will satisfy third normal form if alpha is a superset of beta. There is no problem. It will satisfy it trivially because it will be dependent, fully functionally dependent on the candidate key. If alpha is dependent on beta, then it will be fully functionally dependent on a candidate key, whether it is a prime or a non-prime attribute. If this is not true, then if alpha is a super key, if alpha is a candidate key, then also it's true, because it's in second normal form anyway, because it is fully functionally dependent on the candidate key. If now in the example which we saw here, the first two cases are not occurring in this example. Price to gift item. Here the first case occurs. This alpha, first name and item is a candidate key, so it gives R. But here this is in 2NF, so this condition is not satisfied by either this one or this one. What is this condition? A non-prime attribute is dependent on another non-prime attribute. So a non-prime attribute is functionally dependent on other. So you prevent that one. If you prevent that one, then what other functional dependency can you have? You can have something like this. What can you have? This is not a non-prime attribute. This is not, see, agent is fully functionally dependent on a candidate key. So alpha to R is satisfied here. But in this one, agent to branch code, it is neither a trivial dependency nor is alpha to R satisfied. and if it is in 3NF, then this one cannot be a non-prime attribute, it has to be a prime attribute. Therefore, if this one or this one are not satisfied and the relation is still in 3NF, then each attribute, this may not be an attribute, single attribute, it may be an attribute set, then each attribute in beta must be part of some candidate key. That is, it cannot be a non-prime attribute. It cannot be a non-prime attribute. So that way, this is an alternative definition of 3NF. And we say a relation is in 3NF. So we have got the alternative definition of 3NF. A relation is said to be in 3NF if for every functional dependency alpha to beta on that relation scheme, either alpha is a superset of beta or alpha is a super key, that is a candidate key, or each attribute A in beta is part of some candidate key. Now, what is Boyce-Codd normal form? These two, and these three forms 3NF. Therefore, a relation which is in Boyce-Codd normal form is definitely in 3NF. Any relation which is in Boyce-Codd normal form is definitely in third normal form. So we have got this hierarchy: first normal form 1NF, 2NF, 3NF, BCNF. The next issue is how to get those relations which are not in 3NF. For example, this one is not in 3NF. How do you get it into 3NF? By decomposition. If we want to bring this into 3NF, we decompose it into two relations. One is supplier name item price, and the other is price and gift item. And this is a lossless join, because if you join up, so what we will do, S by will become S name item price 1. This is the first one, and the second one will be price gift item. This is a lossless join because price is a key here, and if we do a natural join, we are going to get back this one. Since price in 2 as 2 supplied by, in the second one, price is a primary key. Therefore, if we do a natural join with this and this, we are going to get back the original relation. Now, this relation is in 3NF. This one is in 3NF because this is the only one which holds here. This one is in 3NF because this is the only one which holds here and price is a super key. In fact, both of them are in BCNF as well. Because in both cases, this one is a super key, in this case, this one is a super key. And so this is not only in 3NF, it is in BCNF, and it is also dependency preserving decomposition. So when we find that it is not in 3NF or not in BCNF, we try to get a relationship which is in BCNF and dependency preserving. Because it is BCNF prevents all redundancies, and if we have it in both BCNF and in which is dependency preserving, we are reasonably preventing redundancy to a large extent and efficiently doing it as well. So this one is one example where we have got it. This is an example which is not in 2NF, which is not in 3NF. And let us try to get a lossless joint decomposition here. How do we get a lossless joint decomposition here? Now this one, agent to branch code. Agent is a super key in B1, and in B2, customer name and branch code, this is the super key. I'm sorry, customer name. We will break it up into customer name and branch code. Why will agent be there? Agent is not. No. This is customer name and agent. This is the correct decomposition. I'll do it again once more. We had the original banker BR code, customer name, agent, and we had agent to branch code and customer name comma branch code to agent. Now let us see two options. The first one is B1 and the second one is the question is, are both of them valid decompositions in 3NF? This one is in 3NF, this one is in 3NF, fine. This one is in, even this one is in 3NF. The question is this one is in BCNF, because this one holds here and this one need not hold anywhere. Here also this one holds here and this one does not hold anywhere. But are both of them correct decompositions? The first question we have to answer is, are both lossless joint decompositions? Look at this one. When you do a natural join, it will be done on branch code. And branch code is not a primary key here. It must be a primary key in at least one of them. If it is not a primary key or a candidate key in any one of them, then the relationship will not be able to get back the original one. For example, this customer here, you will get all the agents For all the branches which have got branch code and all the agents, you will get for this customer all the agents of a particular branch. For example, a customer says Mr. Srivastava may have some Mr. Jain as agent. But here in a particular branch, say Kharagpur branch 0202. Now 0202 may have got 20 agents. So if you do a natural join, this Mr. Srivastava will have all his agents, all the agents coming up here. So this is not a lossless join, this is a lossy decomposition. This one is a lossy decomposition. On the other hand, here agent being the primary key, if this customer name has got a particular agent, okay, customer name branch code will give you agent. Now this customer in 5 branches may have got 5 agents, okay. But for this agent and this branch code, since this is a primary key, if you do a natural join, you are going to get back the original relationship. Just please think over this. This is not a very simple example, but this example highlights whatever we are trying to say till now regarding lossless join. Say Srivastava had agent Jain, and Jain, we know that a particular agent works only in one branch. So if Jain works in 0202, then you will get Srivastava to be in 0202. You have to get it, and Srivastava to get Jain, he must be in 0202 only. If Srivastava has got another, say Sharma, then you are not going to have Sharma with 0202. That is not there in the original relation, because customer name and branch code will give you agent. So in the original relation, you could not have Sharma with 0202. That is, Srivastava with Sharma and 0202 could not exist here. Both Srivastava Jain 0202 and Srivastava Sharma 0202 would be a problem, because Srivastava on 0202 has got only one agent. He cannot have both Sharma and Jain here. So the potential difficulty of having a lossy component, which is this example, cannot arise for this case because of this functional dependency. Therefore, this is a lossless decomposition. So this is a lossless decomposition as well as it is in Boyce-Codd normal form, but it is not a dependency preserving one. It is not a dependency preserving decomposition. So we have now here an example in which you have got two options. Either you get redundancy removed, but then you may not get it in, get a dependency preserving one, or you have a dependency preserving one, which is this one itself, and redundancy will remain. So you cannot have all the options together here, and we will see that at least there is something that you can have. That is, we will see later, you can have 3NF lossless join dependency preserving, or you can have BCNF lossless join. that is, given any relation, you can always break it up into a 3NF lossless join dependency preservation, but we know 3NF still has got some redundancy, or you can get it into BCNF with lossless join. And if we get dependency preservation, it's fine. We would always prefer BCNF lossless join dependency preservation, but that cannot be always guaranteed. So we will first try for BCNF lossless join dependency preservation, and if we see we can't get that, then we will have to make the trade-off whether we will go in for 3NF or we will break the dependency preserving concept. So next we will see two algorithms, one which given any relation will break it up into 3NF, will be able to decompose automatically into a lossless join dependency preserving 3NF decomposition, and we will see another algorithm which will be able to have a BCNF lossless join decomposition. We will see them in the next class.